Hello, welcome to today's class. Today's class will be on shared memory programming. This is the third class on this topic. So far we have seen how to create a process and join processes, and then we saw how to allocate and free shared memory. Then we wrote a program to add all the four numbers in an array using two processes, and in the last class we saw how to use locks for mutual exclusion. In today's class, we will talk about barriers, and we will write a program to compute the mean absolute deviation of an array of numbers. So first, let me explain what we mean by mean absolute deviation of an array of numbers. So let's say there are n numbers in an array, and first thing we will do is sum all the n elements of the array, and then we'll calculate the average, which will be the sum divided by the total number of elements n, and then we will calculate the deviation of each element of the array. So the deviation will be calculated as the absolute value of average minus ai, or it may be ai minus average, doesn't matter because we are taking the absolute value. So we will subtract the average from each element of the array, and then we will take the absolute value of that subtraction, and that will be our deviation. And then we'll add up all the deviation. We calculated the deviation of each element, then we will add all those deviation, and that will be our total deviation. And then we will divide the total deviation by the number of elements n, and that will give us the mean absolute deviation. Let me explain it using an example also. So let's say we have an array. We have 8 elements here. So in this example, n is equal to 8. And when we add up all the 8 elements, we get the sum, which is 56. The next step is to calculate the average. So average is 56 divided by 8, which is 7. Next, we need to calculate the deviation for each element. So we need to subtract this average from each element of the array. So now when we subtract 5 minus 7, we get minus 2. 3 minus 7 gives us minus 4. 2 minus 7 gives us minus 5, and so on. And now we take the absolute value. So absolute value that gives us the deviation. And now we need to add up all this deviation. And when we add up all this deviation, we get the total deviation is 34. And next step is to divide this total deviation by 8. And 34 divided by 8 is 4.25. And that is our mean absolute deviation. So the mean absolute deviation in this example is 4.25. So now if we want to write a program to calculate the mean absolute deviation, these steps has to be implemented in the program, and we can write a sequential program to do this calculation. And the sequential program may look something like this. So in this sequential program, we are first adding up all the elements of the array. We are calculating the sum. Then we calculate the average. Sum divided by total number of elements gives us the average. Next, we need to calculate the deviation for each element. So we need to subtract this average from each element, and that's the for loop for it. And as we calculate the deviation for each element, we are also calculating the total deviation, and then we divide the total deviation by n to get the absolute mean deviation. So this is the program, sequential program, to do the calculation. Now let us execute this program and see the output. So here we have the program. This is the sequential program we just saw. We calculate the sum, then we calculate the average, then we calculate the total deviation, and then we calculate the absolute mean absolute deviation. So let us run this program. And as we run this program, we see that it's calculating the sum as 56, the average is 7, the sum of deviation is 34, and the absolute mean absolute deviation is 4.25. So this is the sequential program to do the calculation. So this was the program, and now in this program, instead of doing the addition sequentially, we can go for parallel program. So there is a scope for parallelization in this loop. So we can divide the total number of elements among multiple processes, and each, for example, we can have 4 processes, and each process will add up 2 elements. And there is scope for parallelization in this for loop also. So these are the 2 parts we can try to parallelize. So now we will write the parallel program, and the strategy that we will use is we'll create 4 processes, and each process will add 2 elements of the array, and the 4 processes will also calculate the deviation of the 2 elements assigned to that process. And this kind of a technique is called loop splitting. So in general, in loop splitting, let's say we have n elements in the array and we have p number of processes, then each process will handle n divided by p elements. So if we have 8 elements and if we have 4 processes, 8 divided by 4 will be 2. Each process will handle 2 elements. And this kind of approach is called loop splitting. In our case, n is equal to 8 and the total number of processes that we will use is 4. But now we have 4 processes. So process 0, process 1, process 2 and process 3. But what are the elements that process 0 will handle? And what are the 2 elements that process 1 will handle? We need to have a strategy for that also. And the strategy that we will use is that process 0 will handle A0 and A4. And these are the array index A0, A1, A2, and these are the values in the array. So the strategy that we are using is process 0 will add A0 and A4. Process 1 will add A1 and A5. Process 2 will add A2 and A6. And process 3 will add A3 and A7. So each process is handling 2 elements each. And so process 0, the ID of process 0 is 0, and process 0 in handle A0 and A4. The process ID for process 1 is 1, and process 1 will handle A1 and A5. Similarly for process 2 and process 3. Now this strategy can be implemented using a for loop like that is shown here. So in this for loop, we increment the loop index by p. So it is not I++, but it is I equal to I plus p. So we start with I, assign the value the ID. So in case of process 0, we will start at 0 and then we will add to 0 we will add p. The value of p is 4. So 0 plus 4 will give us 4. So process 0 will handle A0, then A4, and if we add 4 to 4 we will get 8. So 0, 4, 8, then 12, 16 and so on. For process 1, its ID is 1, so we will start at I equal to 1 and we will go to 1 plus 4, which is 5. So 1, 5, then 5 plus 4 is 9. So 1, 5, 9, 13, 17 and so on. And similarly for process 2 it will be 2, 6, 10, 14, 18 and so on. And for process 3 it will be 3, 7, 11, 15 and so on. However, our maximum value is n is 8, so we will stop at 0, 4 and then we'll stop at 1, 5, because if the value is greater than n we will exit out of the loop. So we see that process 0 will use index A0 and A4, and process 1 will handle the elements A1 and A5 and so on. So this strategy that we thought that process 0 will handle A0, A4, process 1 will handle A1 and A5 and so on, that strategy can be implemented using a for loop like this. So having explained the for loop, now let us write the parallel program. So this is the parallel program which may not be clearly visible. So let me break it up and explain it part by part. So in the first part we initialize the array and we initialize the total number of elements to 8 and total number of processes to 4. Then we allocate a shared variable that is pointed by final deviation, and this shared variable will store the total deviation, the sum of all the deviations that will be stored in this shared variable pointed by final dev. Then we will allocate shared variable, and this shared variable will be used to store the sum of all the elements, and this shared variable will be pointed by total. And since shared variables are involved, to coordinate the access to this shared variable we need lock, and here we allocate the shared memory for the lock. Next we initialize a barrier, and this is the first time we discuss barrier. We will shortly see why we need a barrier. We initialize the barrier here, and then we initialize the lock, and then we create 3 more new process, so that in total we will have 4 process. And once the processes are created, each process will execute this part of the code. And before that, before I proceed with explaining this part of the code, let me go back and let me show you that we have one variable sum, and this is not a shared variable, this is a private variable, and each process will have a copy of this variable sum. And what will be the use of this variable? For example, we saw that process 0 will handle the elements A0 and A4. So when process 0 add A0 and A4, the sum of the partial sum A0 and A4 plus A4 will be stored in this private variable sum of process 0. Similarly, process 1 will handle A1 and A5. So when process 1 add these 2 elements, the sum of these 2 elements will be stored in the private copy of sum of process 1. So each process will have its own copy of sum. Now let's go ahead and talk about this part of the code. As I said, this part of the code will be executed by each process. So in total we have 4 processes. So this part of the code will be executed by each of the 4 processes. And now what process 0 will do? This is the for loop we just now discussed. So when you're talking about process 0 in this for loop, process 0 will add up A0 and A4, and the sum of A0 and A4 will be stored in the private copy of sum in process 0. Similarly, when process 1 executes this loop, process 1 will add A1 and A5, and the sum, this partial sum, will be stored in the private copy sum of process 1. Next, once each process calculates the partial sum, that will be updated into the shared variable pointed by total. As we discussed, the shared variable pointed by total will store the sum of all the elements. So each process will update their partial sum into the shared variable. And since we have a shared variable, the process must first acquire the lock and then only update the shared variable. Otherwise, we will have the problem that we discussed in the last class. And now we have a barrier. So why do we have this barrier? Is the barrier is needed as we do not want any of the process to move ahead until all the processes are done updating the shared variable pointed by total. So what we mean by that is, let's say process 0 has updated its sum to this shared variable, but the other 3 process 1, process 2 and process 3 have not updated their sum. So after process 0 updates, if it do not wait in this barrier and if it goes ahead, it will calculate the average using a wrong sum, because when it is calculating the average, this shared variable only has the sum of process 0. The sum of process 1, process 2 and process 3 has not yet been updated. So if we don't prevent process 0 from going ahead, process 0 will calculate a wrong value for the average. So we want that process 0 should not go ahead, and that's the reason that we have a barrier. So after process 0 updates the shared variable, it will get stuck in this barrier and it will wait for the other 3 processes to arrive. So process 1, after process 0, maybe process 1 will update the shared variable, and then again process 1 will come and wait in the barrier. Process 1 also should not move ahead, because if we allow process 1 to move ahead, right now the total sum has the sum of only process 0 and process 1. Process 2 and process 3 has not yet updated the shared variable. So we should prevent process 1 also from going ahead. So as all the processes updates the shared variable, they will come and wait in the barrier, and that is the purpose of the barrier. So all the process will come and wait in the barrier, and they will keep on waiting till all the process arrive here. So once all the 4 processes are done updating the shared variable, when all the process arrives at the barrier, only after that they will move ahead. And once all the 4 processes arrive at the barrier, it means the shared variable has been updated by all the 4 processes. So we now have the total sum in the shared variable. So now we can allow the processes to go ahead and calculate the average. And once all the 4 processes arrives at the barrier, only after that they will move ahead. So that's the purpose of the barrier. So after all the processes reach the barrier, each of the process can move ahead and calculate the average. Once we calculate the average, next step is to calculate the deviation. And Again, we will parallelize this part. So we have 4 processes, and each process will calculate the deviation for 2 elements each, and that's why we have the same kind of a loop, for loop, that we discussed earlier. So process 0 will calculate the deviation for A0 and A4, and it will store the partial sum of the deviations in this private variable and deviation, and then process 0 will go ahead and update the shared variable that stores the total deviation, and each process will do that. Process 1, process 2 and process 3 will do this calculation, and each of them will individually update the shared variable for total deviation. And then again, join process, again we will wait for all the process to arrive, and after join process, 3 of the process will be killed, and only one of the process will remain, and that process will go ahead and print the mean absolute deviation. So this is the program, parallel program, to calculate mean absolute deviation. So now let us run this program and see the output. Here is the program. As just now we discussed, so we have the barrier, we have the shared memory allocation, we initialize the lock, we create 3 new processes. Each process calculates the partial sum, each process updates into the shared variable for total sum, and all the process will wait. Each process will wait for all the other process to arrive. After all the process arrives, we will calculate the average. Then each process will calculate the deviation of the elements allocated to each process, and each process will update the total deviation, the shared memory for total deviation. We will join the processes, and then we will calculate the final mean absolute deviation. So now let us run this program. And as we see, here is the average calculated by each process: process 0, process 1, process 2, process 3. So all of them calculates the correct average, and the mean absolute deviation is 4.25. So we are getting the correct output. Now just to show the use of the barrier, let me show this program. So it's the same program that we just now saw. Only thing is I have commented the barrier, which means I will not use the barrier. So if I don't use the barrier, each process will not wait here. After it updates the total, it goes ahead and calculates the average. And since, for example, if process 0 updates the shared memory for total sum, after it updates the total sum, it will go ahead and calculate the average. So we may have a problem because of this, as process 0 has updated the total sum does not mean that process 1, 2, 3 have updated the total sum. So my total sum is still not complete, and if I try to calculate the average, I will get a wrong average. And let's see if that will happen or not. So I compiled the program, and now I run the program, and when we run the program we see that problem. See, the average calculated by the first process is not 7, it is something else. Similarly, the second process that arrives that does the calculation for average also get a wrong value for the average. Only the last process gives the correct value for the average, because by the time the last process calculates the average, the total sum has been updated by all the other processes. So only the last process gets the correct value for the total sum. The other process did not get the correct value for the total sum. It was only a partial sum, and that's why the average calculated by them was not correct, and hence the final mean absolute deviation is also not correct. So if we don't use the barrier, our program gives the wrong output. I hope through this example it is clear why we need the barrier. And that's all for today's class. If you have any questions on this part, please send your questions through Piazza. I'll send you these programs. You can also execute them. Okay, thank you. Bye.